Good day, and welcome to the Geo-Institute Technical Committee's web conference. Today's topic is geo-environmental engineering. This is an audio web conference. You will hear the presentation through your computer speakers, and there will be a PowerPoint presentation that will be shown throughout the meeting. You can ask a question through the online web conference tool at any point during the session by clicking the Ask Question button on the left of your screen. Type your question into the box and hit the Send button to submit a question. I'd now like to turn the floor over to today's facilitator, Joe Scalia. Sir, the floor is yours.
Wonderful, thank you. So thank you, everyone. Good afternoon if you're on the East Coast. Good morning if you're on the West Coast. Two of our presenters are in China and Singapore, so I guess good morning to you both since it's now Saturday. On behalf of the Geo-Institute Geo-Environmental Engineering Technical Committee, welcome to the 2018 Geo-Environmental Engineering Web Conference. The conference will run for 2 hours. We have 5 presentations today, but first I'd like to thank our gold sponsor, Keller, for sponsoring the web conference. The connected companies of Keller in North America are uniquely positioned to handle the most complex geotechnical construction projects nationwide. By including all services in one contract, Keller reduces client risk and ensures all aspects of a project are met on time and on budget. So thank you, Keller, and you can see all the high-quality companies there under the Keller banner at the bottom of the screen. So as I said before, we have 5 presentations today. The first presentation is by myself with work done with Craig Benson at the University of Virginia. Jim Hansen and Nazli Yesler are then going to be talking about the evaluation of uncovered GCLs, or geosynthetic bottom liner systems at a landfill. Jianan Chen is going to be talking about bentonite polymer composite geosynthetic clay liners for coal combustion product leachates. Junchang Fei is going to be speaking to us about changes in shear strength of municipal solid waste in landfills due to degradation. And then finally, Kevin Foy is going to be enlightening us on subsidence risk mitigation in LLW final covers and giving us a case history. So many presentations to look forward to, and with that, I'll introduce the first presenter, which is fairly easy. I'm the first presenter. So my name is Joe Scalia. I'm an assistant professor at Colorado State University. You should just now be seeing my first slide, and I'm going to be talking today about an evaluation of an evaluation of subgrade water content on GCL hydration and hydraulic conductivity. At CSU, my research interests really are environmental containment systems, tailings and mine waste, and unsaturated soils. So this research topic, this presentation topic, is something that intersects a lot of those, and I'm looking forward to presenting. So with that, so the arc of this presentation is around geosynthetic clay liners, and we've got a few presentations today about GCLs, as we're probably all going to abbreviate them. And so I'm going to spend a few minutes here just going through some background on GCLs. Geosynthetic clay liners, if you aren't familiar, are factory-manufactured hydraulic barriers. They're typically used in place of, say, a compacted clay liner, either due to faster installation or limited local availability of clay, or for a reduced volume because a GCL is typically going to be on the order of about 1 centimeter and will provide the equivalent hydraulic performance to a much thicker compacted clay layer. So on the top left of this slide you're seeing, I've got a typical cross-section for a geosynthetic clay liner. A GCL is a layer of ground-up sodium bentonite. And so sodium bentonite is a high-swelling, high-plasticity clay, and that's sandwiched typically between 2 geosynthetics. And we might add other components to that system, as I'll talk about. Here I have 2 non-woven geotextiles. And so we end up with a product that's about 1 centimeter thick. We bring it out to the field, and we're just able to unroll it and overlap it. And so the bottom right is a GCL roll being unrolled in the field in a cover, and the top right is the seams being overlapped to create a low permeability hydraulic barrier. The function of a GCL relies on the low hydraulic conductivity of the sodium bentonite layer that is the mineral component of the middle of that system. And so for the sodium bentonite component to have a low hydraulic conductivity, initially it's deployed as a dry powder or a dry granule, typically maybe the size of a fine sand up to a medium sand. And if that system weren't to hydrate, it would have a very high permeability, very high hydraulic conductivity. But for sodium bentonites, when the granules are exposed to water, they swell and they form a gel, and that gel then immobilizes much of the water in the system, creates really narrow and tortuous flow paths and a low hydraulic conductivity. So the pictures here in the middle, I have a photo of a GCL hydrated with deionized water. The scale is in millimeters. And on the right, I have the same GCL hydrated with a high concentration calcium-rich water. So a GCL will get a really low hydraulic conductivity because of that sodium bentonite layer, typically on the order of 10 to the minus 11 meters per second, 10 to the minus 9 centimeters per second, if that gel forms. If that gel does not form, if conditions exist that prevent the formation of that gel, we'll maintain that either small granules or sand-sized granule structure, and we'll have a much higher hydraulic conductivity. And that hydraulic conductivity can be orders of magnitude higher. An example, the photo on the right would have a hydraulic conductivity greater than 10 to the minus 7 meters per second, or 4 orders of magnitude greater than a GCL with a low hydraulic conductivity. And this is going to be really important to understanding how these systems are used in barrier applications. So I'm going to go a little bit deeper, and then we'll get back to the case history and field application. But a little bit more background becomes necessary to understand the field behavior we observe. So sodium bentonite hydrates in 2 domains. The first domain is called crystalline hydration, and this is the first 4 layers of water molecules that wet the mineral surface and hydrate the mineral. And this hydration results in some swelling of the clay, but not a huge amount. And so if only crystalline swelling occurs, I don't form a gel structure unless I'm under a high stress. And so under a low stress, I'll have a high hydraulic conductivity. However, as I continue to add water to the system, and if it's a sodium bentonite or a bentonite in which a monovalent cation is present, I'll also get a process called osmotic hydration and osmotic swelling. And that will result in the immobilization of a substantial amount of water and a low hydraulic conductivity. And so the plot here is just interlayer spacing between individual montmorillonite platelets. Montmorillonite is the key mineral constituent in bentonite, versus the square root of concentration. So as we move to the right, we're looking at more dilute solutions. As we move up, we're looking at more swell. And so dilute solutions, we have lots of swell. Concentrated solutions, we have much less swell. And what's really important here is if instead of a sodium bentonite, I have, say, a calcium or a magnesium bentonite, I can end up with a system that doesn't ever attain osmotic swelling and will have a high hydraulic conductivity. And unfortunately, divalent cations are thermodynamically preferred over monovalent cations in the environment. And so even though I'm going to install a product that's originally monovalent, depending on the pore fluid chemistry, eventually it might become a divalent clay. And so if it hasn't swelled by the time it gets there, that may or may not be a problem in terms of hydraulic performance. And so that's what I'm going to be talking about today. GCLs are typically used in 2 applications. Let's see if I can push to the next slide. Here we go. One application is in covers. So a low hydraulic conductivity layer can be a critical component of preventing that bathtub effect or preventing the generation of leachate due to percolation of precipitation. And so in a cover application, we'll use a GCL to provide that, often under a geomembrane in what's called a geocomposite barrier system. We can use that same barrier system in a bottom liner application. Here I have a leachate collection system immediately overlying a geomembrane, immediately underlain by a geosynthetic clay liner. And so in both these systems, I have the GCL forming a redundant component of the barrier system. The geomembrane is limiting the cross-sectional area through which flow is occurring, and the GCL is providing low hydraulic conductivity for the little bit of liquid that makes it through the holes that may be incurred in the geomembrane. Under the GCL in both these cases, I have a subgrade. And this subgrade is critical because the subgrade, when I have a geomembrane overlying the GCL, is where the GCL will get its water. And it's also where the GCL may get calcium or other divalent cations as it hydrates. So to look at how a GCL behaves in the field, you have to go out into the field. And so we've undertaken a campaign at more than 7 sites where we've gone out into the field and exhumed GCLs that have been in place for a number of years under different site conditions and looked at what is the condition of the GCL, what is the hydraulic conductivity, which ultimately is the engineering parameter we care about for the GCL. So this process is pretty fun for those of us in academics, get out into the field and get our hands dirty. Here you see removing cover soil. This is from an LLW facility. Excavator help. You need to be careful not to puncture the geosynthetics, and so the excavator is only a little bit of help. It gets off the top layer. After that, we need to do it by hand. And so after removing the initial cover soil, we have to manually remove the soil down to the geosynthetics to prevent puncturing or damage of that system, as shown here. The excavator can still be useful as a place to shovel the spoils to so that then it can lift them out of the hole. We continue that process until we get down to the geosynthetics. Dr. Benson can be seen here working on pulling back a geocomposite drainage layer that was placed over the geomembrane to prevent excess pore water pressures. And you can see that geomembrane exposed. You can see the test pit. And once we expose the geomembrane, we'll pull that back as well, and we'll uncover the geosynthetic clay liner. We'll then take sampling plates and mark out the perimeter of the samples we want to take. And while that GCL is still intact on the subgrade, we'll cut out samples with a sharp razor knife. Here you can see Dr. Benson cutting out samples. And then we'll take those samples and we'll carefully transfer them to the sampling plate. And so delicate sample removal here. You can see the concentration on Dr. Benson's face as he's carefully trying to remove this without deflecting the sample, without disturbing the sample to the greatest extent possible. We'll then take that sample, we'll wrap it in plastic, typically load it in a box full of soil to provide a little bit of overburden and also protect the sample during transport back to the lab. And we'll survey the location of the sample prior to leaving. And there's a little bit of extra earthwork you can see on this photo. Here we're also taking undisturbed soil samples of the subgrade that underlaid this location to look both at the geosynthetic clay liner, but also the condition of the underlying material. And as part of this process, you can take samples of the upper geosynthetics as well. One last piece to add here, we've done this at a number of sites. Typically these sites have been in cover applications, and that's just because a cover tends to be much more easy to access in the field than a liner. Folks tend to be reluctant to allow you to dig up the waste and expose the liner. Covers, if you can time them right while there's a lateral expansion occurring, turn out to be much better in terms of opportunities for sampling. So here's a photo of a GCL exhumed in the field. And this GCL has that nice hydrated gel structure that we're looking for. This is a good sign. This next photo is from a GCL exhumed at a different field site. And you see the bentonite isn't fully hydrated. In fact, it's only at about a 35% water content. And so we have that retained granular structure. So depending on if this is a calcium bentonite or a sodium bentonite, if it's a sodium bentonite and it's permeated with something dilute, it'll swell and still have a low hydraulic conductivity. If it's a calcium bentonite, even if it's permeated with something dilute, it won't attain that low hydraulic conductivity. So we took these samples back to the lab, and in the lab we ran hydraulic conductivity tests. We measured the water content of the GCLs. We looked at the water content of the subgrade. And what we found, here is a plot of hydraulic conductivity versus the exhumed gravimetric water content of the bentonite component of the GCL. We found that the subgrade water content and the GCL water content are very important relative to the hydraulic conductivity. So hydraulic conductivity here, we have higher hydraulic conductivity when we have lower GCL water contents as exhumed from the field, and we have low hydraulic conductivities when the GCL had a high water content. So what we observed was if we had rapid hydration, sufficient hydration in the field, we got a low hydraulic conductivity dilute solutions, and there was a strong relationship between hydraulic conductivity and water content. How do you get a GCL wet in the field? Well, the answer looks to be you put it on a wet subgrade. And so we observed a linear correlation between the exhumed gravimetric water content of the GCL and the subgrade water content shown here relative to the optimum water content under standard Proctor conditions. So when we were at or wet of optimum, we observed a low hydraulic conductivity. When we were dry of optimum, we observed a high hydraulic conductivity. And that tied to the GCL attaining a high moisture content or a low moisture content. So this was nice. We had some field data. We had some hypotheses. We wanted to explore a little bit further this behavior. And so we went back to the lab to look at if our hydration race hypothesis was correct. And the hydration race hypothesis is just what I've said. There's a race when a GCL is put on the subgrade because as the GCL pulls water from the subgrade, calcium molecules that are native in that subgrade pore water are also going to come along. And so if we end up with too many of those calcium molecules and too much exchange of the native sodium for the preferred calcium, we can end up with a divalent or a calcium bentonite before a low hydraulic conductivity is achieved because we haven't hydrated the bentonite yet. If, however, we hydrate the bentonite sufficiently before there's cation exchange, that hydrating water stays in the system, and so we maintain a low hydraulic conductivity. And so we decided this race analogy, we want to hydrate it first before there can be before there can be too much calcium exchange. It's really a good way to think about the problem. And so we need to ensure conditions during installation that ensure this hydration race is won by hydration and not by cation exchange. To figure out the conditions that occurs, we set up a bunch of laboratory hydration tests. In these laboratory hydration tests, we compacted a subgrade at different moisture contents, put a dry GCL on top, applied an effective stress for a closed system, and then after some period of months, we exhumed the GCL and tested the moisture content and the hydraulic conductivity. What we found was that dry subgrades, as we had observed in the field, yielded rapid hydration to a equilibrium, maybe a low equilibrium, and then not a dramatic increase in water content. In contrast, if we hydrated on optimum water content subgrades, we tended to observe rapid hydration to a much higher GCL water content, and that water content was retained. And so this hydration behavior is really occurring rapidly, and we also observed that our field water content was basically mirrored by our laboratory hydration. I've got lab hydration data shown and field hydration data. And for our dry field condition, we didn't have a wet field condition, so we can't look at field hydration under wet conditions, but we saw correlation there. We then looked at the hydraulic conductivity, and as we had seen before, our optimum water content, green triangles here, maintained a low hydraulic conductivity. In contrast, rapidly, our dry subgrade hydration achieved a high hydraulic conductivity, not what we want from a barrier layer. And this range of hydraulic conductivity mirrored what we observed in the field. So incomplete hydration, we also observed cation exchange, yielded this high hydraulic conductivity condition. This behavior has been since looked at by a number of authors, and here's a correlation of our data and some other data. And what we see is to get a GCL to a high gravimetric water content, typically we need to place it wet of optimum. And I say typically, and the shortcoming here, right, is that the engineering behavior is, of course, more complex. So to just say we need to place it wet of optimum isn't a full story. There's two data points here for GCLs hydrated on clayey subgrades that had a high smectite content, very analogous to the montmorillonite, which is a smectite component of the GCL, And in these systems, the GCL, even though it was placed on the subgrade wet of optimum, didn't attain that high degree of hydration on that clayey subgrade. So engineering judgment and knowledge needs to be used in this design. We can't make a blanket statement that it always has to be wet of optimum. There's a water balance here, and there needs to be thought put into if I'm placing a GCL on a sand or a silt, maybe even a low plasticity clay, that needs to be wet of optimum. If I'm placing a GCL on a high plasticity clay that's really going to have a lot of competition for water with the bentonite, I need to make sure that GCL is on a subgrade that's wet enough that the GCL will get water, and that subgrade probably needs to be even wetter than wet of optimum, and that's what we're seeing from the data. So the take-home message here is get the GCL wet, keep the GCL wet, and in dilute conditions, the data show so far that that will maintain a low hydraulic conductivity. And some of the later presentations in this web conference are going to talk about what happens when we're permeating with high concentration solutions. So finally, I would like to end with a couple poems, a couple haikus from my graduate environmental containment systems class. Engineers, we spend a lot of time writing. It's fun to watch students try to compose poetry related to geotechnical engineering. And so with that, I'd just like to thank Dr. Benson. Our contact information is on this last slide, the National Science Foundation and SETCO for providing funding for this study. And then I'd just like to add that a lot of this research was done while Dr. Benson and I were at the University of Wisconsin. So thanks to the University of Wisconsin. All right. With that, I will open it up to questions from the audience. So as was said before, if you have questions, type them in. We get a little pop-up that says the specific questions and lets us know what the audience is thinking. All right. So looking here, one of the questions is, what is the threshold concentration where hydration of a GCL will make sure that you have a low hydraulic conductivity? So it's not a cut and dry answer there. Really, a hydraulic conductivity test is needed to ensure that there's compatibility between the permeant solution and the GCL. And that permeant solution needs to be tested with the specific GCL that's going to be used in the field, with the effective stress that's going to occur in the field, really to make sure that under the site-specific field conditions, you're going to have a low hydraulic conductivity. And so a blanket recommendation, get it wet, keep it wet, is probably an oversimplification. There needs to be assurance that site-specific tests are conducted and that those site-specific tests provide a low hydraulic conductivity. Let's see. Other questions. Wet subgrades are difficult to construct due to rutting. Might it be easier to add water right before placing the liner? Great question. So in terms of construction, really we're recommending kind of near optimum or a little bit wet of optimum. And I think the question is absolutely correct. Making sure the subgrade isn't too wet to prevent rutting means you can't just say get it as wet as possible. There needs to be a balance there. Another option certainly would be to add a dilute water to the GCL, but then the risk is really run that if you hydrate the clay becomes very soft, and so then tremendous care has to be placed when placing material above the GCL to not squeeze the bentonite around and result in thinned layers that are going to have a high hydraulic conductivity. So ideally, a subgrade that's wet enough to hydrate the GCL but still able to be worked on. And if that isn't practical due to site-specific conditions, adding enough water to the bentonite and then being very, very careful not to disturb the bentonite when additional layers are placed on top. Let's see, another question. Won't a GCL that has equilibrated on a low water content subgrade that is subject to infiltration from above, e.g. from a leak in the overlying geomembrane, then swell, reducing the hydraulic conductivity to a lower value? That's a great question also. So if the GCL hasn't equilibrated or has equilibrated to a low water content, then when infiltration reaches it, if it's a sodium bentonite still, it will exactly hydrate and retain or achieve a low hydraulic conductivity, which will then seal off that hole in the overlying geomembrane. The problem is if the GCl is able to exchange before that downward percolation reaches it. And so we saw that rapid hydration to a low water content and then rapid achievement of a high hydraulic conductivity in, say, the first 100 days with some of our GCLs hydrated on a dry subgrade. And so if the race is lost and cation exchange occurs before hydration, then you might have a condition where then when infiltration is added, you don't have a low hydraulic conductivity. All right, if anyone has any further questions, I'm out of time. Feel free to contact me. My contact information is on this last slide. And with that, I would like to move ahead to the next speaker. So our next speaker is Jianan Chen. Jianan is an assistant professor at the Department of Geoscience and Environmental Engineering at Southwest Jiaotong University in China. Jianan holds a PhD in geological engineering from the University of Wisconsin at Madison. His main areas of interest include the performance of hydraulic barriers in landfill liners and the recycling of industrial waste at structural fills. So with that, I think I went to the wrong order here. My apologies. Our next presenter is Jimin Nosley Hansen. My apologies, Jimin Nosley. So Jianan, I know it's midnight there, but I'll make you hold on a little bit longer. So Jimin Nosley, Jim Hansen, is a professor in the Department of Civil and Environmental Engineering at Cal Poly San Luis Obispo. Nosley Yesiller is the director of the Global Waste Research Institute, also based at Cal Poly San Luis Obispo. So with that, my apologies, Jim and Nosley. Jim and Nosley are going to be providing our next presentation.
Hello, good morning, everyone. I will be starting with some background related to investigation and then turn it over to Jim. Thanks, Joe, by the way. In this case, we were looking at the condition of an uncovered geosynthetic bottom liner system that was exhumed at a landfill. Some of the material that I will go through actually will reflect on what Joe had said earlier and closely related to some of the observations that he had made. Composite liner systems, including geomembrane, geosynthetic clay liner composites, are used commonly for different types of containment facilities. GCL use is common in place of compacted clay liners due to a number of advantages of the GCLs, including low hydraulic conductivity to water, low thickness, resistance to environmental stress, and ease of installation. Even though composite liner systems have been used extensively over the last 2 decades or so, concerns and uncertainties exist in the performance and effectiveness of these materials, especially in the long term. To ensure successful application and use of these systems, timely cover is critical, as is the case for pretty much all different types of geosynthetic materials. The 2 main issues for exposed geomembranes are, first, formation of wrinkles due to thermal cycles resulting from diurnal temperature changes, and aging and degradation of the polymer-based plastic materials due to UV radiation and oxidation. The main problems for exposed GCLs include dimensional stability, resulting in shrinkage of individual GCL panels, separation along seams, and formation of gaps between the panels, migration of bentonite, uneven bentonite concentration in the GCL installed at a site, and variation in moisture content of the GCL and the chemistry of the bentonite component of the GCL. Our field investigation included observations of condition of the geomembrane GCL composite that was installed at a landfill and was left uncovered for an extended period of time. The field site that the investigated is located near San Luis Obispo along the central coast of California. Some details about the site include that it's a Subtitle D municipal solid waste landfill. The site has permitted area on the order of 49 hectares for waste placement. The facility is located in a temperate climate zone with dry and warm summer. And some statistics, climate-related statistics for the site for the exposure period include the mean annual temperature on the order of 16 degrees C, mean minimum and mean maximum on the order of 9.1 and 22.5 degrees C respectively at the site, and the mean annual precipitation of 415 millimeters during the exposed period. The composite liner system at the site was installed in 2004 and consisted of a geomembrane placed over GCL. The geomembrane was a black HDP, high-density polyethylene geomembrane that had one side textured and the other side smooth. The textured side was placed facing down towards the ground, immediately above the underlying GCL, and the top smooth surface was exposed to the atmosphere. The GCL was a middle-punched product which had granular bentonite that was sandwiched between two nonwoven geotextiles, and in cross-section was very similar to the GCL that Joe showed in his presentation earlier. The liner system was exhumed in 2016 after 12 years of exposure to the atmosphere. The intended application for this bottom liner system is shown on the schematic on the left side of the slide. From bottom to top, the geomembrane GCL composite was placed. There was to be a leachate collection and removal system placed above this layer, a separation layer, and waste was to be placed above this separation layer. The actual constructed system is shown on the right side of the slide and consisted solely of the geomembrane and GCL system. And the liner materials, the barrier system, was not covered at any time during this 12-year exposure period and was exposed to the atmosphere, including temperature variations, high solar radiation due to the generally sunny conditions in California, seasonal rain events, as well as periodic wind events. At this point, I'm going to turn the presentation over to Jim to provide details of our field investigation.
Thank you, Nazli, and thank you, Joe. This is an aerial photograph of the cell that was exhumed, at least the portion of this liner, and the north arrow is shown there nominally on the right, and the darker portion, that lower slope, kind of making a J shape, is what was removed, and I will refer to those as the east slope, being the long portion of that J shape, and the south slope, being that smaller triangular version off to the left. And the lowest portion of the curve I will term corner, just for reference in a couple of photographs coming up. To start with, let's look at the site geometry. And this photograph that's loading here, just a moment, is showing an image taken from the corner that I discussed or described. And the slope length ranged from 24 to 30 meters. And this was a relatively steep slope at 2 horizontal, 1 vertical. And I'll move from here to identify the exhumation process that was undertaken. This was done by a contracting crew. And the process involved peeling back the geomembrane first in given panels and leaving the GCL exposed for a portion of the slope. It was during that period that our research crew had an opportunity to observe the status of the seams, take some additional samples of the GCL at that time, and make observations about the subgrade as well. And the GCL was rolled down the slope. You saw that crew in the previous slide rolling it down. They do that for a portion of the slope and then let it roll by gravity, the remaining. In terms of observations of that exposed system, the geomembrane was undergoing significant wrinkling and had wrinkle heights on the order of 15 to 20 centimeters in height, producing a gap between the geomembrane and the GCL. Overall, the geomembrane, had uniform appearance, and this applied to both the parent material and the seams, and significant defects or degradation was not observed visually through our observations. The difference in membrane behavior between a morning session or nighttime and daytime was significant. You see an image here, a photograph. This, by the way, both of these images are looking toward that corner that I highlighted in the overhead view. We see in the morning that membrane is tight as a drum. And in the afternoon, due to the sun exposure and increase in temperature and thermal expansion of that product, wrinkles are formed. And again, these are of significant height. And somewhat relevant on our related project, speaking of diurnal changes, I just returned from an all-night run at a landfill here in California. We had a research crew of 8 persons out at a landfill from 1 to 4 a.m. doing some gas emissions measurements. As many aspects of landfilling do have diurnal aspects, so we're looking at that currently. The sampling of the geosynthetics took place before or during removal process, and the geomembrane was done before any construction activity had begun. And this was a somewhat treacherous activity. We had harnesses and roping and so on for our crew. On that 2-to-1 slope with very smooth surface, it was surprisingly slippery and difficult to traverse. And we identified locations on the slope at the top, middle, and bottom of the slope locations and cut out coupons, similar to what Joe had shown for the coupons being cut out of those GCLs. A concern that exists with these seams and panels in this exposed condition is shrinkage of the panels, and seam separation can occur. And in the observation of that entire slope, which consisted of 43 seams, we noticed 8 gaps, and that was along 7 different seams. And this means that one of the seams contained 2 separate gaps. And the gaps ranged between 20 and 220 millimeters in width and a length between 1.7 to 17 meters. And I have an image here of an example of one of those gaps. It was rather considerable. And you can see some red dots along the edges of each side of that gap. And those are placed by the manufacturer in terms of guidance for an intended overlap of these seams. And that's the state of the practice for seaming these products, is simply an overlap on the order of 200 millimeter distance. And certainly here, the panel shrinkage has overcome that amount. And the close-up image in this case shows a gap width of 150 millimeters or 15 centimeters. We've done significant work in a laboratory setting related to quantifying this behavior, this panel shrinkage and dimensional stability through wet-dry cycling, and did some work in relation to preparing GCL specimens at different water contents and observing the difference in behavior. And with water contents ranging from as received, nominally 15% water content, up to 150% water content, quite hydrated, we had linear strains measured due to shrinkage of 10 to 14% in these. And we'd go through cycles with this. 20 cycles were being done and monitoring the shrink swell over those cycles. Through this, we identified, or for practical comparison, we identified what we termed a panel shrinkage threshold, a PST, and identified that 1.3% linear strain in the machine direction or 3.3% linear strain in the cross-machine direction would be sufficient to cause a gap, respectively, in those directions. In terms of observations of the GCL composition, the GCL had non-uniform appearance throughout locations at the slope, and variable moisture content was observed as well and measured. The bentonite, as well as some subgrade soil, had migrated, and in different locations we had migration and actual accumulation of these separate products, bentonite and subgrade soil. From a moisture content perspective, this is a photograph of a coupon being cut out of that GCL in a dry condition near the top of the slope and maintained a granular consistency. And we brought some back to the laboratory for side-by-side comparison, and we see here towards the crest of the slope or the top of the slope, we have a dry condition GCL maintaining this granular consistency, and towards the toe of the slope, we have a wet or gel-type structure where that had been hydrated more properly. The migration of bentonite was observed through streaking on the top of the GCL, and this is significant in terms of what's been reported by others in terms of this phenomena. And it leaves behind rivulets that contain the bentonite, and then these dry to provide these permanent streaks on the top of the GCL. And these were extensive across many sections of the slope. And on the right photograph, you see an accumulation of bentonite right at the toe. That shoe is actually standing at the toe of the slope. So we're pulling up the geosynthetic products there of that composite liner and viewing an accumulated mass of bentonite at the toe of the slope. And we quantified that accumulation and termed this a wedge because of the characteristic shape that it took on. It's nearly 3 meters in length, that's along the slope, and the accumulation height at this highest point, which was right at the toe of the slope, was 90 millimeters, nearly 4 inches high of bentonite accumulation. This is quite significant in terms of quantity of bentonite, leaving some regions further up on the slope devoid of bentonite, literally just 2 leathery pieces of non-woven geotextile. In comparison, on the southern slope, we had that wedge, by the way, was occurring on the east slope is where we measured that. On the southern slope, we had subgrade soil accumulation, and we term this a mountain, again, due to its characteristic shape. And this also was a significant amount of material, again, extending nearly 3 meters in length, and the height on this was 160 millimeters. So in summary, the atmospheric exposure of a composite liner system has significant effects on a bottom liner system. And timely cover certainly is relevant in this case, and avoiding this situation altogether is prudent. Geomembrane wrinkles are present due to diurnal temperature cycles of an exposed system. Bentonite migration and loss from the GCL does occur. Bentonite and soil both accumulate, in this case, was observed to accumulate towards the toe of the slope. And we did have some issues near the sump where there was ponding occurring, and we feel that may have attributed to the mountain shape rather than the wedge shape that we noticed with the, or observed with the bentonite. Some additional analyses are underway, including quantitative analyses on geomembrane and GCL, and many of these have been completed. Significant variations have been observed in the properties. These have been reported in Quo et al., the Geosynthetics Conference, in terms of geomembrane oxidation in induction time. The GCL mass per unit area, water content, swell index, and hydraulic conductivity are reported in a paper in Williams et al., 2018, just to be presented this fall. The geomembrane mechanical properties are being conducted currently, and the GCL cation exchange capacity and mineralogy have been completed and will be reported elsewhere. We'd like to acknowledge Waste Connections Incorporated and the landfill site staff for access and cooperation with this project, the Global Waste Research Institute for providing partial funding, and a collection of researchers that assisted with the fieldwork and some of the graphics in this presentation. Thank you, and I welcome questions at this stage. Now, Glenn. And wonderful. One remaining slide, we do have some references that were cited during this presentation that I'll leave on the slide for the moment.
Great. Thank you, Jim and Nosley. Jim and Nosley, looks like we have about 3 minutes to go through some questions.
Okay. Joe, would you like to bring them on?
Sure. So one of the questions, don't current recommendations for GCLs in composite liner systems call for covering the composite liner shortly after construction? Isn't it unacceptable to leave such a liner uncovered for 12 years?
That would be the case under current regulations, and that is a portion of the reason this was not reutilized. They actually were expanding this site out. The site geometry was changing, and that was a large part of the rationale on removal of this system. But the site operations were quite unique here in somewhat giving up on this cell location. But it provides a very unique opportunity for addressing long-term exposure of such a system.
But timely cover is, of course, it's something that should be done and is required to be done, and in this case was not done, and that's why the liner system was being exhumed, and we had an opportunity to go in and collect some samples. It wasn't, this liner system is not going to be used, it's not being used.
All right, and next question, how do you handle this in your construction specifications?
I think that just having some assurance that cover is occurring and some additional provisions such as heat bonding of GCLs has been recommended. That could be something to consider in addition as, one more dimension of prevention in terms of causing or preventing, the separation of the panels. But I think the construction QA/QC would be most important. Just assure that on the order of 1 foot of sand, 300 millimeters of sand is placed or more. And that should generally take care of the diurnal cycling.
Interesting. Well, thank you, Jim and Nosley. It looks like there's a few more questions that we don't have time to go through. So Jim and Nosley, I believe, will be attempting to reach out to you and answer these questions if your questions haven't been answered. So with that, I would just like to thank you one more time and introduce Jianan Chen, our next presenter, for a second time. Jianan, as I said before, is an assistant professor at the Department of Geosciences and Environmental Engineering at Southwest Jiao Tong University in China. He holds a PhD in geological engineering from the University of Wisconsin-Madison, and his main research areas are the performance of hydraulic barriers in landfill liners and recycling industrial waste as structural fills. So with that, Jianan, I'll leave the floor to you.
Thank you, Joe. So thank you, everyone, for participating in this web conference. Today, I'm going to cover my research topic, that is bentonite polymer composite geosynthetic clay liners for co-combustion product leachate. This study is mainly conducted during my PhD study in University of Wisconsin. First, I would acknowledge my co-authors, Kulia Salihoglu, who is working in Golder right now, and my advisor, Dr. Benson, my research committee, Dr. Lykos, and Professor Edo. Okay. So co-combustion product, also known as CCP, is one of the largest waste stream in the U.S. It's normally including the bottom ash, fly ash, and flue gas desulfurization gypsum, which is also known as FGD. Sometimes people use inject Chona powder into the flue gas to help reduce the sulfur, and also it produces the Chona ash. All this material gonna be should be either beneficially reused or properly managed in the on-site management facilities. So according to the statistics, in 2012 in the U.S., it about 110 million tons of CCP generated in the 47 states and Puerto Rico. Also in the country, China, that also relies on the thermal power, it produces about 350 million tons of CCP in 2006, and this quantity increased to 580 million tons in 2014. So we can see there are a lot of CCPs generated in the U.S. and China. So as I mentioned before, this material going to be properly managed in on-site, for example, landfill or surface impoundment. Sorry, this is loading right now. So based on the new rules of CCP management, the management of CCP should in accordance with the rules in Subtitle D. And Subtitle D requires using a composite liner system. That composite liner system including a layer of geomembrane and a layer of compacted clay liners. The compacted clay liners should have a thickness about 0.6 meter of thickness. This compacted soil clay liners can be replaced by the alternative liner materials such as the geosynthetic clay liner, which is also known as GCL. And Joe and Jim already introduced a lot of background on the GCLs. And in our group, we also have conducted research on geosynthetic clay liner and compacted clay liners and the compatibility to the CCP leachates. So the GCLs, traditional GCLs containing sodium bentonite as the main component, because sodium bentonite can swell when contact with water and reduce the hydraulic conductivity, which has hydraulic conductivity lower than 10 to minus 11 meter per second. It also have a simple rapid installation, this kind of benefit. However, based on the previous studies and our study, when the sodium bentonite GCL contact with CCP leachate, it has some issue with the incompatibility to the leachate chemistry. For example, the incompatibility including the cation exchange, high ionic concentration of the leachate, and perhaps the extreme pH conditions. All these kind of conditions will suppress the swelling of the bentonite and leave high hydraulic conductivity of the GCLs. So the manufacturer has worked and studied along to produce some material that has better chemical resistivity. They have studied to use modified bentonite to provide higher chemical resistivity to the leachates. So this is only an example that we're showing how this works, because the modified bentonite has very complex mechanism. This is only one example. Right now, many manufacturers uses dry mixing polymer with bentonite. The polymer can hydrate and form hydrogel and works in the bentonite mixture and stay in the bentonite porous media. However, this compatibility of BPC GCLs to the CCP leachates is not well studied. So based on our understanding, we create 3 objectives for our study. So the first one is to identify the chemical characteristics of CCP leachates that give rise to incompatibility with GCLs. The second one is to assess the chemical compatibility of BPC GCLs with the CCP leachates. The third, of course, is to study the mechanism controlling the hydraulic conductivity of BPC GCLs. To fulfill the 3 objectives, we conducted our research step by step. The first step is to understand the leachate chemistry of CCP leachates. So we used a database from APRI that provided some information on the CCP leachates from their management facilities. These facilities including landfill or surface impoundment. In the database, you can see from this slide, it included like code types, disposal types, site average of leachate chemistry. This database including 38 landfill and surface impoundment. We use only the leachate data, which is the sample collecting from the leachate collection system, or the water collected from the pore water. I mean, pore water means pumping from the waste. So based on this data, we calculate the ionic strength and the RMD using visual MinTech to understand the leachate chemistry. Because the leachate chemistry are very complex, we simplify this leachate into 2 simple parameters. Why these 2 parameters are very important? Because based on our study, ionic strength and RMD, which is relative abundance of monovalent to polyvalent cations, it indicates the tendency of cation exchange. So the lower RMD and high ionic strength of solution will negatively impact the hydraulic conductivity of sodium bentonite GCLs. So we think these 2 parameters will also have a negatively impact on the BPC GCLs. So after translate all the leachate chemistry into these 2 parameters, we create a figure that showing the RMD versus ionic strength that give our visually very easier to understand the leachate chemistry. Here, which we based on this database, we choose 5 synthetic leachate. So I'm gonna show them all here. So the 5 leachates, including 2 typical CCP leachates, which represents the typical case of all the leachates of CCP leachates, or typical case of the FGD. Also, we choose 3 other leachates that represent the worst case of the leachate. They have either high ionic strength or lower RMD. Beyond that, we also selected 3 site-specific leaches, because these site-specific leaches have high ionic strength, and they showed worst-case scenarios, and we're gonna encounter this kind of leachate in the design. So we also included these 3 leaches into our investigation. The material we use, including 9 samples of GCLs. So the first 2 GCLs here are 2 samples of sodium bentonite GCLs. We use the sodium bentonite GCLs here to understand the baseline hydraulic conductivity and make the comparison to the BPC GCLs. And we also use 6 samples of BPC GCLs here. They are dry mix. They are manufactured by dry mixing bentonite and polymer together. And beyond that, we also selected 1 IBPC GCL. That is, the GCL is manufactured by in-situ polymerization. Here, I don't know if you can see the slide. Here's a table that's showing the name of the samples. You may notice that there's a number on the sample label. The number indicates the polymer content of each BPC GCL. For sure, for the sodium bentonite, there's a 0% of polymer content. When you see the BPC and IBPC, you will see that indicates the polymer content by the loss on ignition method. The testing method here for the hydraulic conductivity, we used the falling head constant tailwater K-test. The tests were running on all the GCLs to CCP and DI water to the chemical equilibrium. Chemical equilibrium means the effluent has a similar chemistry. Okay, here's the results. Here's the results showing the hydraulic conductivity of GCLs to the leachate chemistry. So we can see the black dots here, black circles here. It shows the sodium bentonite. We can see in the shadow zone, the traditional sodium bentonite has the hydraulic conductivity directly related to the ionic strength of the leachate. When you have higher ionic strength, the hydraulic conductivity of sodium bentonite also increases. Also, when we plot the BPC GCLs with low polymer loading, you may find it also behaves like sodium bentonite. However, when we plot the BPC and IBPC GCLs onto this figure, we can see at a certain point, here is the ionic strength less than 755 millimolar. It shows the hydraulic conductivity was all lower than 1 times 10 to minus 10 meter per second. And beyond that point, you can find a high hydraulic conductivity, which can be higher than 10 to minus 8. That follow a step function. We want to understand the mechanism. So the traditional mechanism of controlling hydraulic conductivity, the swelling, we see the sodium bentonite, the hydraulic conductivity directly relate to the free swell. And also for the BPC GCLs with low polymer loading, which is the green color circle, open circle, it also follows similar trend. However, when we plot the BPC and IBPC GCLs onto this figure, we can see the low swell, you can still have a high, low hydraulic, when we have a low swell, you can still have low hydraulic conductivity. Low swell here means less than 16 milliliter per 2 grams. You can still have low hydraulic conductivity, about 1 times 10 to minus 12. 10 to minus 12. So we want to understand the mechanism it certainly shows different controlling mechanism. Here, I want to cite my colleague's work, colleague Tian's work, because we are using the same GCLs. He used low-level radioactive leachates and he did the image analysis, and he found the polymer actually have a clogging mechanism and work just as just clogging the pore space of the bentnet. When the polymer contact with water, it tightly bound with the water and form high viscosity hydrogel that fill up the void and give low hydraulic conductivity to the BPC GCLs. However, this is the polymer should have enough. The BPC GCL should have enough polymer in there to be functional. Based on our study, when polymer loading is less than 5%, we can see a large variability of hydraulic conductivity of the GCLs. It varies 4 to 5 orders of magnitude. When the polymer loading increases higher than 5%, we can see generally the hydraulic conductivity is lower than 2 times 10 to minus 11 meter per second. And there's only one exceptional is the test that with the strongest leachate. Strongest means the leachate with highest ionic strength, that is CCP3 leachate, that has high hydraulic conductivity. Also, we observe some interesting point is the retention of the polymer is very critical for the BPC GCL to be functional. During our test, we find out some of the GCLs when permeated with strong leachate, its hydraulic conductivity increase over time. This temporal behavior correlate with the effluent total organic carbon content. We can see there's a large quantity of TOC eluted over the initial time. The first 2 PVFs and continues till 35 PVFs. And to quantify this, we correlate the hydraulic conductivity to the cumulative polymer elution. We can see about more than 50% of polymer was eluted. Actually, this eluted polymer leave up pore space, and the hydraulic conductivity has increases about 3 to 4 orders of magnitude. To sum up this presentation, I have a few conclusions here. So first conclusion is the BPC GCLs can have much lower hydraulic conductivity than sodium bentonite GCLs when permeated with CCP leachates. And the hydraulic conductivity of BPC GCLs depends on the chemistry of the leachate, polymer loading, and probably the type of polymer and bentonite. Mechanism of controlling the hydraulic conductivity of BPC GCLs and the sodium bentonite differ depending on the polymer loading. And retaining polymer hydrogel in the pore space is critical for BPC to maintain low hydraulic conductivity to CCP leachates. Here are some publications from this study, and I would thank my sponsor, APRI, SACO, and University of Wisconsin and University of Virginia, and I am welcome for your questions. Thank you very much.
Thank you, Jianan. All right. So, questions for Jianan? I think we have a little bit of feedback just due to the transatlantic echoes, or trans-Pacific, I guess, echoes. One question for you. It would be interesting to check the total organic carbon of a BPC GCL with a higher polymer dose and lower hydraulic conductivity.
Yeah, so that's sorry, Joe.
No, go ahead.
Yeah, That's an interesting question. So, this leads to our future work, and we are exploring the mechanism more deeply, and because we right now here we run the test because there's an obvious increase in the hydraulic conductivity of the GCL. It shows an increase of 4 orders magnitude of the hydraulic conductivity, and we correlate this to the TOC, and we'll do in the future to see the low hydraulic conductivity GCLs. Yeah, for sure.
Great. Thank you, John. And it'll be interesting to hear what happens to those low hydraulic conductivity GCLs in future presentations. All right. With that, to stay on time, John, thank you again for your presentation. And our next presenter is Xinchao Fei. Xinchao graduated with an MS and PhD degree from the University of Michigan in Ann Arbor under the supervision of Professor Demetrius Zekos. Professor Zekos is also the chair of the Geo-environmental engineering subcommittee for Geo-Institute. So thank you, Dr. Zekos, for your time. Dr. Xinchao then worked as a postdoc researcher with Professor Carlos Santamarina at King Abdullah University of Science and Technology in Saudi Arabia, and he is currently an assistant professor at the School of Civil Engineering at Nanyang Technical University in Singapore. His research interests involve environmental and energy geotechnics. So with that, I'll leave the floor.
Hello. Well, thank you everyone for attending this web conference. Let me start my slides here. All right, well, today I'm going to talk about or present some of my PhD work with Professor Zekos at the University of Michigan. The title will be Changing Shear Strength of Municipal Solid Waste in Landfills Due to Long-Term Degradation Process, Long-Term Coupled Degradation Process. So the outline of this presentation is fairly simple: introduction, methodology, some of the results, and then come to the conclusion. First, I want to again show you guys this very simple or very straightforward plot that's about the waste generation problem. Waste generation disposal is a worldwide challenge because, well, here I'm showing the waste amount of waste generation in the United States per year. It's more than 350 million tons. And similarly, sorry, let me go back to the slide and show the animation here. I apologize. All right. So similarly for China, we have similar amount of waste generated per year, but here I'm also showing the difference in the disposal method. For the United States, around 50% of the solid waste is actually sent to landfill. For China, it's about 60%. And for the European Union, although they have more or less the same amount of waste that's being generated per year, they have a different disposal strategy. So the waste that has been landfilled is around 40% per year. But nevertheless, I would say landfilling is always, well, at least in the near future, will be a major disposal method for municipal solid waste worldwide. So let's look at some of the modern landfills. Modern landfills these days are actually becoming huge infrastructures. So these two photos I'm showing now, right on the left, are not landfills, but they are so-called gigantic infrastructures that people usually know. One is the Fort Peck Dam, which has a huge volume. The other one is the biggest open mine or open pit mining site in the United States, the Bingham Canyon Mining. But what is surprising to maybe some of you is that some of the largest landfills in the States have like even larger volumes and footprints than those very famous and well-known infrastructures. For example, one landfill in California, which is I think it's closing now. It has a volume that's way exceeding the containing or the capacity of the Fort Peck Dam. The other very famous landfill located in New York State has a bigger footprint than the Bingham Canyon mining as well. So overall, landfills are becoming really huge facilities these days, and we need to take good care of them. Well, why I say take good care of landfills is because we know from time to time landfill failure will happen. Here I show 3 different photos for 3 pretty famous cases of landfill failures. The first one on the top left is the Rump landfill failure, which happened in Ohio. It's primarily due to weak shear strength weak interface shear strength between the solid waste and then the clay liner, which ties back to some of the other presentations today. And there are 2 more pretty famous cases happening in Southeast Asia, one in Philippines and the other in Indonesia. Both cases, the waste slid because of shear strength failure, and in both cases, actually, a lot of people were killed. So landfills are still not safe infrastructures. They have many shortcomings, or we have to really think about how to design a landfill safely for a very long lifespan of a landfill. So our research questions here at the University of Michigan are, first, does shear strength of municipal solid waste change throughout its lifetime in a landfill? Because, when the waste is disposed of in a landfill, it stays there almost forever for decades or to even up to centuries. So the change in shear strength is definitely one thing we need to think about or take into consideration during our design. And the second question is, what is the impact of long-term coupled degradation processes on solid waste shear strength? Because, again, when the solid waste is disposed of in a landfill, it undergoes many different processes because it's exposed to different elements, and the microbials are actively degrading the waste. The third question is, what's the impact of initial waste composition, or say regional difference, on municipal solid waste shear strength? That's because, worldwide or even between different states in U.S., the waste composition is very different. In order to answer these 3 questions, my research group, my advisor, and I, we first started with a field campaign for solid waste sampling. We started from Michigan and then traveled all the way to Texas, to Arizona, and eventually reached California to basically dig out waste, put them in the drums, and ship them back to the laboratory. I want to bring to your attention one more thing is that if you look at those photos for different landfills, you will probably very vaguely see that the waste composition and in the cover system, they have different colors. That is an indication of different waste composition and different waste management practice. And that has something to, just keep that in mind, because later on I will also tie back to this point. So when the waste is shipped back to the lab, we first started with a very detailed waste characterization. So the waste is taken out, saved to 2 major parts. You can see on the top left photo here. One is the smaller than 20 millimeter sieve material, and the other major part or major fraction are the bigger particles. And then the bigger particles are further separated into plastic, paper, and wood, and some other big objects like gravels and metal pieces. So for each of those wastes, we weigh all these different fractions to get a field waste composition, and then remix a part of that waste to form a specimen. And each specimen is loaded into a simulator, as shown on the photo in the right. So each simulator has the slide is loading. All right, each simulator has a volume of about 40 liters, has a height of 0.6 meter and a diameter of 0.3 meters. So it's fairly large, as in the lab, as containing, well, it's a lab simulator, and it's sealed. So after it's sealed, isolated from the oxygen to simulate the anaerobic landfill condition, leachate is added to the waste, and then to the leachate is recirculated a few times a week to accelerate biodegradation process. So as you can see on the right, the leachate chemistry is carefully characterized. But again, well, this is not the focus of my presentation today, so I'm going to just very briefly show some of the figures, just demonstrating that we have a very close characterization of what is going on with the waste degradation process. For the biogas, similarly, we collect biogas and do measurements throughout the waste degradation period. And in addition, we also characterize waste, the solid waste itself, primarily the settlement of the waste, the long-term compression index, and also the total weight of the waste using a floor scale. Microbial ecology of the waste is also studied, but again, this is not the main focus of this presentation. So in total, I want to present the results for 4 different simulators, each contain a waste from a different state: Texas, Arizona, California, and Michigan. And in the table, you can see that it's a long-term degradation test. So the shortest one is 900 days, and the longest one is about 1,500 days. They all have different waste composition, different amount of less than 20 millimeter particles. And again, like I said before, this is not the focus of this presentation. So you are referred to this recently published paper for more details. This is another photo showing the initial state and the final state of one of the simulators. And the difference between those 2 red lines are the self-settlement due to biodegradation, just to show that the biodegradation is actually having significant impact on the waste material or on the waste properties. So now we're ready for the solid waste shearing test. And this photo here, or the schematic here, is showing a unique large-size single shear device that we developed here at the University of Michigan. It's in collaboration with the instrument company Geo-Congress. And more details about this instrument. This instrument is a versatile instrument for many large-size samples, and more details can be found in this journal paper that's recently published. But essentially, this device tests a very big sample or very big specimen, a diameter of 30 centimeter and a height of 15 centimeter for simple shear testing. So now let's look at what we did with the solid waste. As part of my PhD work, I tested more than 130 samples, but again, for this presentation, I'm only going to talk about the results for some constant load tests and the minimum compaction effort. The photos on the bottom left here are showing the initial state of the waste specimen and after shearing. So you can see for simple shear, it's contained in the rigid ring, but after shearing, there's a very clear slinky shape of the material. And before shearing, it's like the waste material is like a cylinder. So, sorry, one more second. So for the stress strain curve, so we obtain stress strain curve for each of the waste specimens, and for each stress strain curve, we obtain the shear strength at 10% shear strain, because the full stress is reached at a very large strain, and we think that usually this large strain is not very reasonable in the field, so we took 10% shear strain to as the shear strength level. And now we can do the comparison between the fresh and fully degraded solid waste. So first we prepare some specimens that has identical state and waste composition as the fresh waste, test them in the simple shear device, and then we degrade each of those large waste sample in the simulator for a very long period of time. After that, each of the waste is very carefully retrieved from the simulator, as you can see on this series of photos. And then the waste specimen is moved to the simple shear device for testing. So by doing this, we can isolate all the other effects and only pin down or lock down the effect of waste degradation on the shear strength of the waste. So again, I'm going to show some example results. Here, the black lines are showing the shear strength of the fresh waste. So we took the 10% strain shear stress and then plot this line for the fresh waste. And afterwards, we also obtained, like I said before, the waste strength after degradation. So these are shown in the colored line here, the red and blue line. And for this specific waste, for the waste from this specific site, the Texas waste, we can say that the shear strength is reduced after degradation for between 20 to 35%. But that's not the whole story because, well, this is only one site and we saw shear strength reduction after degradation. What happened to all the other sites with different waste composition? For the Michigan waste, we also saw a decrease in waste shear strength between 0 to 20%, as you can see on the figure to the right. But interestingly, we also saw for some cases increase in waste strength. For example, in this for this California waste, the waste shear strength is actually increased a little, about 10% after waste degradation. And for the Arizona waste, the strength increased even up to 40% in some cases. So we believe this difference in waste strength change after waste degradation is related to the waste composition and also the moisture content and waste structure, waste fabric. But we haven't established a very detailed correlation between them yet. So for this presentation, we just want to show some of our preliminary results. So now let me come to some conclusions. The first conclusion is, yes, of course, the waste shear strength of the municipal solid waste changed throughout its lifetime. And we have to be very aware of that because usually the landfill is designed for decades to centuries. And when the waste is in place, it's very hard to retrofit or to reinforce the waste. So it's better to design a landfill, for especially the landfill slope and containment system in the beginning before the waste is actually in place to make sure the slope will be stable, there's an interface shear strength will be stable, and etc. So we don't have any of the slope failures, which is really costly in many ways. And the long-term normalized, the symbol here is the normalized shear strength, changed between plus minus 35 to 40%. So it's kind of a very large range, a very wide range. But for us, I think for the engineers to design a landfill, we better be on the conservative side. So a conservative estimation is to design the waste to be weaker in the future at about maybe 20% because the decrease in shear strength for like up to above 30% is usually rare, we believe. So 20% strength reduction is a reasonable number to keep in mind. Again, these are not final results. We are still doing some additional analysis. So of course, the waste composition also affects the shear strength significantly, not in the short term, but also in the long term, because waste composition is the key parameter or the key factor in determining how much the waste is going to degrade in the long term. So with all these, I want to conclude my presentation today. Thank you for your attention. And also I want to thank all these funding agencies for my PhD and postdoc work. And also I want to thank my PhD advisor, Professor Akos. And we welcome any questions.
Thank you, Zhenchao. I think you hit the 18-minute timing within a second, so very much appreciated and wonderful presentation. We have a few questions for you. The first one, how do you relate the properties of the waste in situ to the properties measured on a reconstituted sample in the lab? Doesn't waste structure matter?
Yeah, that's a really good question. So it's essentially two parts, right? How do you relate the property of the waste measured? Like I mentioned briefly, we have done more than 100 tests. Some of them are using the field waste unit weight through compaction. But some others are under minimum compaction. What I showed here today are some of the waste that are reconstituted, and they may be looser than the field state. But in general, we have all the waste that are having field composition for sure, because we did very careful field composition characterization, so we know we reconstitute the sample using the same composition. But then the unit weight might be a bit different, that we acknowledge. And the waste structure, of course, matters, but I think we did two things. The first is we always observe what the actual waste composition or waste structure in the field. And usually these are layers, because after all these compaction and threading of the construction machine, these like fibers and soft plastic bags and wood, they are more or less oriented horizontally. And we also did this for the lab specimens as well. So we make sure they are randomly placed in the first place, and then we compact it. And later on, we also check the waste specimen to make sure the fabric is at least similar to the in-situ structure. Although, yeah, you are right that there's no guarantee that the waste structure is identical to the field, but we tried our best to mimic field waste structure and field waste condition, and we believe we did a good job.
A second kind of follow-on question: if waste strength decreases with time, shouldn't older landfills be failing?
Yeah, that's one thing that people can always ask, and even I myself, I asked this question many times. That is, it's always a case-by-case scenario, right? Waste strength may be decreasing, but then is it really hitting the strength envelope? We don't know, because waste, like I said before, waste composition does matter, and it matters a lot for different landfills. So, so usually even the waste strength is decreased a little. As long as it's safe, I think it's just if it's safe and it doesn't fail, people usually don't pay attention to those older landfills. But I don't know what's going on in the future. Well, let's just hope it doesn't fail. And also, waste strength is not like the most important controlling parameter in landfill slope design. So sometimes, maybe a reduction of waste strength for 10% isn't that critical.
Okay.
But again, we always want to know what's going on, so that's kind of the whole driven point or the driving factor for this research project, right? We want to know what's going on so we know everything is under control or not.
Yep. One last very quick question for you. We don't have much time left. For those unfamiliar with landfill design, what is the range of common shear strength values that are used in MSW for the design of landfills?
That's, again, a question that's somewhat, why I'm kind of smiling at this question is because the people above you is actually the one who came up with the most famous landfill shear strength design chart, Professor Kavazenjian. And you can refer to his work for some of the at least baseline shear strength recommendations for the landfill design. What we are trying to do here is, just to kind of put some uncertainty bar for the long term to say that, hey, well, you want to design with this weight strength, but in the long term, just be a little bit careful because the weight strength might change. And you don't always want to just test the fresh weight because you want to keep in mind that long-term degradation also matters for the weight properties.
Great. Thank you, Zhenchang. And with that,
thank you for your attention.
We have our last presenter for the Geo-environmental webinar. Kevin Foy completed his PhD at Purdue University in 2005, completing the sweep of Big Ten universities here in this web conference. Kevin joined CTI and Associates, a small geoenvironmental consulting firm in Michigan, after he graduated. Now he's a senior engineer. Kevin leads the geotechnical engineering practice at CTI and has specialized in landfill engineering and ground improvement using geosynthetics, supporting a large number of infrastructure projects nationally and internationally. So with that, Kevin.
Okay, thank you for the introduction, and thank you everyone for listening. We made it to the final presentation. What I want to do with this presentation is a little bit of a departure from what we've seen so far. A lot of the work that we've seen so far is very good and detailed at looking at very important aspects of things that go into our landfill barrier systems and the waste itself, as we just saw. What I'm going to do next is take a little bit of a step back and look more at the system level and some of the concerns that we have as designers that are trying to construct, in this case, a landfill final cover. And there's a lot of complexity in these systems, and as engineers, there are certain components that we can satisfactorily quantify. But as you saw from the quality of research that's being presented, there are a number of things that we are not yet able to quantify as well as we might like. And so I'm going to focus a little bit on that. Before I get into the details, I want to acknowledge some co-authors that have been working with me over the years on this work. What I'm about to talk about represents a culmination of, I would say, just under a decade worth of development in this concept, in this line of inquiry for the design method. First, I want to mention Mohammed Kavalan, who has helped develop a lot of the larger scale design modeling that I'm about to present. Ramya Rajan was doing a lot of the mechanical studies that we used, some numerical work to try to relate how we are seeing settlement in existing landfills in some large bench scale and full scale studies to two equations, two models that we can actually use in our design analyses. And then finally, Dr. Tiang Sung, who has been working for decades in geosynthetics, particularly in geomembranes, geogrids, other barrier applications such as GCL that we've heard about, and was a major part of pulling this design methodology together and presenting it to the various stakeholders. The outline that I'm going to talk about focus a bit on the project background, so give a sense of how this fits together with the design problem that we were facing. Have 2 bullet points here related to how we go about the engineering analysis of the landfill final cover settlement problem and how that would affect some of the design decisions that we might make. And then talk a bit about design criteria. How do we decide if the analyses that we've conducted are telling us that we have adequate performance or not adequate performance? Because ultimately performance is a benchmark that we want to be able to tie our design decisions to. The project site that we most significantly applied this design methodology to is the Maxey Flats disposal site in eastern Kentucky. And I think it'd be worthwhile at this point to acknowledge the Commonwealth of Kentucky as our primary client in this endeavor and, of course, paid for all of the work. The Maxey Flats disposal site has been for a while a CERCLA or Superfund site that was under active cleanup for quite an amount of time, several decades, to mitigate effects from low-level radioactive waste that was buried there as part of commercial operations that took place in the 50s, 60s, and 70s. The picture that I'm showing here is an aerial view of the site that was taken in the 80s during the startup of cleanup operations at the site under CERCLA. The area under which waste was buried at this site is about 24 hectares in size. Initially, waste was buried in various containers in shallow trenches, and after a while it was discovered that leachate containing tritium was entering the groundwater from the site, and at that point the waste burial activities at the site were discontinued, and cleanup activity including relocation and capping of the waste were conducted with the culmination of final cover that was constructed just a couple of years ago. The picture on this slide is an aerial photo of the site that was taken in the early noughties, early 2000s, showing an interim cap that was placed over the site consisting of an exposed geomembrane, similar to what we heard about before, an exposed geomembrane application that included some stormwater control features to try to prevent the infiltration of stormwater into those shallow trenches and the subsequent percolation and carrying of radionuclides away from the site. That was only an interim measure. It was always envisioned in the long-term cleanup of the site that eventually a permanent cap would be constructed once it was understood the degree to which subsidence would affect future performance. This slide is showing the appearance of the site shortly after completion of the cap, and I'm going to show a typical view explaining what the different components of that cover are. This slide is showing an example final cover, and most of what you're seeing here is shared in common with the final cover that was designed for maxi flats. But I wanted to show it to illustrate some of the major performance considerations we have for final covers, and specifically the role of water in the final cover and how it does or does not enter the waste, which is the primary mechanism with the final cover design that we're concerned about controlling. So at the very top, rainwater that hits the top of our final cover is going to first encounter a vegetated topsoil layer, which is a common feature in many final cover designs. Some of that water is going to run off directly. Some of it is going to enter the plants and then later on be evaporated back into the air. And then some of that water is going to percolate through the topsoil, through our protective soil layer, and eventually into some drainage media, either sand or a drainage geocomposite, that we are going to use to conduct that water off of the cap to where it can be drained and collected away from our barrier layer. Our barrier components, of which we've heard a lot about today, include a geomembrane and barrier clay, either compacted clay liner or a geocomposite clay liner. We are concerned about the possibility of there being holes in our geomembrane that is going to permit water to enter our barrier clay and then from there infiltrate into our waste or other layers of our cover soil. In the case of maxi flats, that would be progressing down to the interim cover before it would enter the waste. As a performance concern, we want to know how much water is going to flow through those holes and ultimately leave the site. Ideally, we would want to quantify just how much flux, just how much radionuclides would be carried away, and ultimately how much of that would either enter vulnerable ecosystems or be consumed by people who may get sick from that water. And there is, in fact, a large line of inquiry in the low-level radioactive waste management community that looks just at that problem, trying to model the system all the way from where water enters the system to where there are potential exposures. That is not the basis for the design that we are doing. The design that we did is somewhere in between fully prescriptive, which is more typical for landfill final cover designs, and fully performance-based, which is still in its infancy. This next slide is showing a picture of what a final cover might look like when it's completed. You can see the grass and the slopes. This is a picture from a municipal solid waste landfill where the final slopes are much steeper than what you would typically see in a low-level radioactive waste landfill where the slopes tend to be quite nearly flat. And also for everyone's reference, the view of a final cover system in various stages of construction. In this case, where we can see the geomembrane layer is exposed and has not yet been covered by the protective soil or the vegetative topsoil. Again, a useful reference for the technology that's being used here. Same technology for a final cover system for municipal solid waste landfills, of which we have lots of design experience. Is very similar to what is being used for low-level radioactive waste landfills. In the case of low-level radioactive waste, the biggest difference that we have between municipal solid waste and low-level radioactive waste is the manner in which the waste is buried. And so this cartoon is meant to illustrate how we might have containers that are placed in trenches and then backfilled. And there are very good reasons for doing this. When it comes to radiation safety, going all the way back to the 40s and 50s, it was recognized that we have to observe sort of the three main concerns about exposure, which is the intensity, the time of exposure, distance from exposure, and shielding, which can be used to mitigate those factors. And so it was understood quite clearly that if you have something radioactive, what you want to do is shield people from it, minimize their time of exposure, and increase their distance, which is exactly what trenches are designed to accomplish. Here's a view of the waste containers being placed in maxi flats in the 70s, not long before the site was shut down. And this is a typical practice at the time, where we have various kinds of radioactive waste that are contained in small containers, which may ultimately be placed in the drums. Those drums then sealed and put into the landfill. You may also have boxes and other things. The Maxi Flats site took waste from, I believe, more than 60 responsible parties, including the Department of Energy, a number of universities and hospitals and other sources. That included everything from research-derived waste to medical waste and other sources of radioactive waste. And in that process, in the interest of limiting people's time of exposure, those wastes will be placed into various containers. Those containers have air in them, and what we're concerned about when we're looking at the final cover is the possibility of those voids then later collapsing and causing subsidence at the ground surface. This cartoon is showing a modified view of our trenches, now with the containers in place and the cover soil placed on top. As those containers age and potentially collapse under the weight of the cover soil, we're going to see depressions. Those depressions are going to preferentially occur over the places where waste is buried in these trenches, and specifically in the discrete locations where we have container collapse, resulting in potential depressions at the surface. Those depressions would allow the buildup of water. That water would then provide the source of a gradient to push water through our holes in our geomembrane and then percolate through the final cover and into our waste, which is a condition that we're trying to minimize to an acceptable level. So that's the overall problem. Understanding where our differential settlement is coming from, what is a practical way to go about modeling that differential settlement, given that we are talking about millions of containers spread over a large area, much of it unknown in its exact composition and void space. How do we go about modeling that? Building upon my background, the decision was made that we will do this using a probabilistic framework, and switching to a probabilistic framework introduces some other concerns that I'm going to talk about in the remainder of this presentation. So I have a flowchart that I've put on the screen, and this flowchart outlines the large picture view of our design process. Design process includes a data review to try to understand what types of waste that we had at the site, understand what kind of containers were there, and from there estimate what kind of void collapse are we going to expect in the future, which would directly feed into estimates of settlement and drainage as part of our design analysis. Before we can conduct that model, though, looking at the upper right part of the flow chart, we have some other things that we need to think about. We need to think about how that void collapse occurs mechanically, how are those void collapses transmitted to the surface. We had two models that we developed in the course of doing that work. I'm not going to focus a lot on those models. I'm going to focus more on the outcome of them. We had two models. TSS model is an acronym we came up with. It's simply a finite difference model of deformation of a thin cover system over a void in the ground. From there, we went into a more generalized volume loss model that is looking at how we translate changes in volume in the ground to depressions appearing at the ground surface, trying to connect what we're doing at the macro scale to very large bench and full-scale field tests that have been conducted at other sites. one of the things that we were looking at doing is reinforcing our final cover to limit the spread of this deformation. So we're looking at geogrid reinforcement. We have to consider creep. We have to consider local reinforcement design. That's ultimately going to go in how we size that reinforcement system. But in the center of a flow chart is the heart of the design decision, which is for a given amount of settlement and the resulting drainage, how do we decide if it's acceptable or not, and how do we iterate our design through a combination of cover thickness, cover slope, and reinforcement to arrive at an acceptable design. So I'll talk a little bit about reinforced final cover analysis. This is pared down from the details, given the amount of time that we have. These are the kinds of effects of subsidence that we see at the ground surface. We see different depressions ranging from wide abstract shapes to very specific discrete shapes in the case of containers that have collapsed near the surface. These can be related back to things that we see also at municipal solid waste landfills, where we're translating MSW consolidation to depressions at the ground surface, and then other examples shown in this slide as well. What we're interested in is what is the occurrence over different areas across the site of different amounts of subsidence. And to condense a lot of work into a very small slide, it is possible to come up with a distribution that is sensitive to the kinds of waste, how far along in the process you are, what kind of containers you're dealing with. Ideally, we want to quantify these things very detailed, but if you don't have a lot of detailed information on the distribution of those parameters, you can go to a random field model, which is what we did. And the question then becomes, if I use a probabilistic random field model, how do I decide if the settlement that I'm seeing in my model is acceptable or not? And that's where the design criteria comes in. Using prescriptive designs from MSW practice across the country, we went ahead and built a model of an example landfill, looked at what kind of subsidence we would see at the surface based on our calibrated models to case histories, and see what distribution of pooling of water we would see on top of that cover. This chart that I'm showing in the slide right now shows an aggregation of several hundred simulations of that example landfill. The reference criteria with the black line here is showing the cumulative relative frequency with different 30-centimeter floodings across that site. So on the x-axis, how much area is flooded to 30 centimeters. On the y-axis, what is the cumulative frequency of that occurring across our models? So moving from left to right, we are seeing that as we have a larger and larger flooded area, those larger percentage of flooded area represents a smaller portion of the expected number of outcomes. So that's a probabilistic measure. So if we have, in this case, those bar charts for actual design that we produced plotting above that line, it means it's acceptable because compared to our prescriptive design, we are having less ponding or ponding to a lesser degree than we are in our reference criteria. And that's how we went about coming up with our design criteria. What this means practically for design is that we would be running several different combinations of slopes, cover thicknesses, and reinforcement until we arrive at a combination that both passes our design checks and optimizes our cost as far as those other components that I mentioned. I'll give you an example visually of what some of these simulation runs may look like in the case of Maxi Flat specifically. What you can see in this aerial view is a shaded view of where depressions are going to occur at the ground surface based on what we know about the distribution of the waste and the trenches that the waste is placed in. But of course, the way that settlement is going to happen in the future is not guaranteed. It's not deterministic. It could happen in different ways, and so we had several different 100 runs to anticipate the different ways in which that waste may settle and produce depressions at the ground surface. Ultimately, we settled on a combination of slope, reinforcement, and cover thickness that would limit the deformations to an acceptable degree of pooling compared to that reference performance criteria. Again, not explicitly tied to exposure as ultimately we want to do, but one step closer to being able to accomplish that. Final comment, by having GeoGrid, we were able to increase the spread of that deformation over a larger area, so we have less deep ponding. which is ultimately our goal to try to prevent that infiltration. Some pictures of everything being placed. We had 2 layers of geogrid. Here's the bottom one being placed on top of that interim cover. We see vehicles spreading the protective cover over the top of our barrier system. Eventually, topsoil and grass being placed to achieve the final appearance of the site today, as we see on this slide. A couple of final remarks. As many of our presenters have said, landfill final covers need to perform for a long time. We have clear performance objectives that we want to accomplish, some of which we can adequately quantify, some of which we cannot. What we were doing in this work is taking a probabilistic design approach that allows us to better quantify long-term performance in terms of settlement, which is not something that we have much tools to do at the moment. And then the purpose of this case history, of course, to get a satisfactory design, but also to illustrate here how we might go about applying this probabilistic approach to sizing this landfill final cover. Okay, I have one comment here saying that it was a nice study. Thank you, I appreciate that. Another question, how did we do the landfill settlement simulation analysis, finite element or finite difference, 2D or 3D? This is a great question. So I had to skip over a lot of things in the interest of time. What I can say in this flowchart is that we went from doing a finite difference model at a very small scale initially to make sure that our predictions of translation of changes in volume in the ground to the surface were being modeled correctly. That was done using finite difference. We went to a more generalized model that's essentially like a tunneling deformation spreading model for the site-wide analysis over the 24-hectare site. And that was highly simplified. The reason for doing that was so that we could run hundreds or thousands of realizations with a random field model where we were simply altering the occurrence of those void collapses inside the waste trenches across the entire site. So, long answer to a short question. We started out at the small scale using more sophisticated numerical analyses. We went to more simplified numerical analyses at the site scale once we were convinced that they had been adequately calibrated. I hope that answers your question.
Thank you, Kevin. Perhaps a final question for you. How has the final cover performed since it was constructed?
So indications that we've had from the site, and they do have a fairly rigorous monitoring program out there where they're walking the site regularly and looking for deformations. To my knowledge, no major deformations have been noted. However, the plan is, should they get major deformations, they are going to fill those with soil so that they continue the runoff regime that they want to have for this final cover.
Great. Thanks, Kevin. So with that, we've made it through our 5 presentations. I'm going to wrap up. We're right at our 2 hours. And one last time, thank our gold sponsor, Keller, for sponsoring this Geo-Environmental Engineering Web Conference. And I'd like to thank all the presenters for taking the time to put these presentations together and provide 5 very interesting presentations. And then finally, thank all of you for dialing in to listen. If you have any following questions, I think all the presenters are open to hearing from you. And if you cannot get a hold of any of the presenters, please just let me know, and I'll try to connect you. So with that, thanks, everyone, and have a great rest of your Friday.
Thank you. This does conclude today's conference. We thank you for your participation. You may disconnect your lines at this time and have a wonderful day.